Today we're just going to cover some basic properties of simple harmonic motion. SHM for simple harmonic motion. I'll be using that abbreviation pretty regularly. Periodic motion is any motion that repeats itself. It repeats itself in a set amount of time. So any motion where the same thing happens every X number of seconds, that kind of motion would be classified as periodic. Period is the variable t, and period is the time for one cycle. So I think we already talked about that when we talked about gravitation. We discussed what period is. Frequency, you might know, but I don't think we've talked about it in this course yet. It's the variable f. It is the number of cycles per second. So this is time for one cycle. This is cycles per second. There's an inverse relationship between those. Frequency is 1 over period, or period is 1 over frequency. Angular frequency doesn't have exactly a nice definition like that. It is omega, and it's very closely related to angular velocity. Angular velocity is how many radians per second an object rotates through. Angular frequency is very closely related to that. If you take a periodic motion and you treat its period as being a full cycle, as being 2 pi radians, then that's kind of have an idea of what angular frequency is. Formula is 2 pi f or 2 pi over period. So those are just some definitions. Period, time for one cycle, t. Frequency, number of cycles per second, f is 1 over t. Angular frequency is 2 pi f or 2 pi over period. So those are some quantities that are important in any periodic motion. Simple harmonic motion specifically is a type of periodic motion that is caused by a restorative force that is proportional to displacement from equilibrium. And what does that mean? Well, restorative means it's going back to where it was before. That's what restore means. You're going back to a previous state. So restorative means it points back toward the equilibrium position. So if we have an equilibrium position, mass is over here, the force will push it back toward that equilibrium position. Then when you get over here, again, that force will always point back toward the middle. And then it's proportional to displacement from equilibrium, meaning that if you're half as far away, then the force is going to be half as big. So if you go twice as far out, the force is twice as big. And then what that winds up causing is if you move an object away from this equilibrium, restorative force that's proportional means that it'll be pushed toward equilibrium faster and faster, and then as soon as you get here, the net force at equilibrium is 0. And as soon as you get to the other side, we start having a force in the other direction. It gets bigger and bigger until the object comes to a stop, and it's just going to oscillate back and forth over that equilibrium position. Because of this peculiar type of force, a force that is directly proportional to displacement from equilibrium, a graph of simple harmonic motion position time graph is going to be sinusoidal. The reason for that is the best explanation is based on calculus, but I'll try to analogize as best as I can to explain where that comes from. Sinusoidal means, is sort of shaped like this. Depending on what's happening, it could potentially be a cosine or a sine graph, though we will more often use the cosine. So typically, a simple harmonic system will be moved some distance from equilibrium, then released. And what function would that be? Well, if it's moved some distance from equilibrium and let go, it's going to be pushed back toward equilibrium right away, which means it's going to have its maximum displacement at t equals 0. All of you have done this by now in pre-calc, or you took pre-calc in the past. And a sine-like curve that has a maximum at t equals 0 is a cosine function. And then cosine functions, well, what properties do they have? Well, they have an amplitude, which is a maximum displacement from equilibrium. Remember, amplitude is that. From the maximum point to the middle point is the amplitude of a sine or cosine function. And then the period is determined by, some function of time, the period is determined by this coefficient. It turns out this coefficient is actually the angular frequency of the function. In general, if you're just thinking about any old cosine function, there could be what's called a phase shift, where you add or subtract something inside the cosine function. But if we're moved some distance from equilibrium, then released, if we're starting directly at a max, the phase shift is 0. So we have that. And in physics, we have the advantage of being able to set our axes wherever we want to. So wherever our system is at, we set the middle of that to be our 0 for x, or y, depending on what direction our system is rotating. And so then we don't have a shift of the graph up or down. We don't have to add or subtract anything. So the general format for position as a function of time is a cosine omega t. Any sort of sinusoidal motion, a way to analogize that is if we track the x-coordinate of a particle undergoing uniform circular motion. So if we take this to be our axis, we've got a particle going around in a circle. Pretend that's a good circle. This is our object, and it's going around that way, counterclockwise. So at some time, say at t equals 0, we want to start at the x-axis because we have a maximum at t equals 0, maximum displacement. At some later time, we've traveled through some angular distance theta. Well, what's the x-coordinate of this? Well, we have the radius of the circle, and doing some trig, that x-coordinate is going to be equal to r cosine theta, right? Well, r is the radius of the circle. For simple harmonic motion, we don't have a circle. We call that amplitude. So the r becomes a. And if we're undergoing uniform circular motion, we have constant angular velocity, which means that theta, we can say, is just equal to omega t. So you can see how that relates to uniform circular motion. In the same way, we can derive an expression for velocity as a function of time based on uniform circular motion. Got our same circular motion. Say we want the velocity at a given point. Well, the velocity is always tangential, right? And if the angular position is theta, the tangential velocity, we draw some axes. Okay, this is theta. That means this is 90 minus theta. That means this is theta again. That means this is 90 minus theta, which means this right here is theta. Okay, so if we want to find the x-coordinate of the velocity, that's going to be velocity times, well, this theta is from the vertical. So the x-component, first off, it's going to be negative because we're pointing back the other direction. And that's going to be the side of this little triangle that is opposite the angle. So that's going to be negative v sine theta, whatever that velocity is at that time. And what is velocity? Well, we know for uniform circular motion, V is equal to R omega, and we already established that our theta is equal to omega t, so our velocity then as a function of time for simple harmonic motion is negative. R becomes amplitude, so it's negative A omega sine omega t. For those of you that have calculus, you might notice that this is the derivative. Velocity is the time derivative of position. Derivative of cosine is negative sine. And then because of chain rule, we multiply an omega to the outside. If you haven't taken calculus, that didn't make sense, and feel free to ignore it. Now notice this is a trig function. We know the value of sine, or you should know from your math classes that the value of the sine function oscillates between -1 and 1. So the maximum value of our speed, the magnitude of velocity, the maximum value is when this is 1. So the maximum velocity is just A omega for a particle undergoing simple harmonic motion. Okay. Now, similarly, we can think about acceleration. Draw our circle of particles right here. What direction is the acceleration? Well, I said it's at uniform circular motion, which means speed is constant, which means our only acceleration is going to be centripetal. Centripetal acceleration, we know, points toward the center of the circle. So let me go over here so we can draw this a little bit bigger. Our acceleration points toward the center of the circle. And we know this angle, again, is theta. So this is going to be 90 minus theta, which means this is going to be theta right here. So this acceleration vector, the x component of that is negative A times cosine of theta. All right. Now this acceleration we know is centripetal. And we know centripetal acceleration is equal to v squared over r, which is also equal to omega squared r. So what does that give us? Acceleration as a function of time is negative. Remember, for simple harmonic motion, radius is replaced with amplitude, omega squared, cosine, and as we have done before, we know our theta is equal to omega t. So that is an equation we can write for the acceleration as a function of time for our simple harmonic motion. And again, for those of you who have taken calculus, you can see that this, if you take a time derivative of our velocity function, you get the acceleration function. And just like our velocity, just like sine, cosine has a maximum value of 1. So the magnitude of the maximum velocity is just the amplitude times omega squared. And remember that omega is related to the period. So if you're given information about the period, you can find the angular frequency and use that to, well, write all these equations and calculate different values related to them. So